Space travel sounds like a round trip, but it isn't. The moment you leave Earth, return stops being simple and starts becoming a fragile fight against physics, biology, time, and distance. And the farther you go, the less real the idea of coming back becomes. On Earth, a return trip feels normal. You go somewhere, you come back, end of story. That is how daily life works, so your brain carries that same idea into space. But space travel is not built on the logic of daily life. It is built on physics, and physics does not care about your plan to come home. The second you leave Earth, return stops being a normal part of the journey. It becomes a small, temporary possibility that only exists if speed, fuel, timing, hardware, and conditions all stay on your side. That is the part most people miss. On Earth, moving around feels easy because the planet keeps covering for you. Air slows you down, roads guide you, gravity is stable, machines can stop and restart, and help is usually nearby. In space, none of that is true. Every change in speed costs propellant. Every correction uses up margin. Every mistake stays with you. There is no road, no air to break you gently, no quick rescue, no natural environment trying to keep you alive. So the whole emotional idea of go out then come back starts breaking down the moment you apply it to space. And that leads to the bigger point. Earth is not just where you live. Earth is the system that keeps you alive every second. Your body is not designed for a planet. It is designed for this planet. You're adapted to 1G, about 9.81 meters per second squared, or 32.2 feet per second squared. Your muscles, bones, heart, blood flow, balance, and posture all depend on that pull. You're adapted to sea level pressure around 101 kilopascals. You're adapted to an atmosphere that is about 78% nitrogen and 21% oxygen. You're adapted to a magnetic shield that helps block harmful radiation, to liquid water moving through a huge binding biosphere, to microbes in your body that evolved with you, and to a day-night cycle set by a 24-hour rotation. So leaving Earth is not just travelling to another place, it is leaving the only full environment your species has ever been shaped to survive in without machines. That is why space is so brutal. The danger is not only outside you. The danger is that your body expects Earth in thousands of ways all the time, whether you notice it or not. So here is the next hard question. If Earth is doing that much work for you, how extreme is even the easiest version of space travel? Low Earth orbit sounds close, because in one sense it is. The International Space Station circles at roughly 400 kilometers, about 250 miles above Earth. On a globe, that sounds like almost nothing. It sounds like you are barely off the surface, and that is why people underestimate it. They hear 400 kilometers and think nearby. But orbit is not defined by height alone. Orbit is defined by speed. To stay in low Earth orbit, a spacecraft moves at about 7.66 kilometers per second, around 17,100 miles per hour. That is more than 22 times faster than a commercial jet. It is roughly 15 times faster than a rifle bullet. So astronauts are not just floating above Earth in some quiet, gentle environment. They are moving at enormous speed, constantly falling around the planet. That phrase matters, falling around the planet. A lot of people think orbit means escaping gravity. It does not. Gravity is still doing the work. The spacecraft is falling toward an Earth the entire time, but it is moving sideways so fast that the surface keeps curving away underneath it. That is what keeps it from hitting the ground. So even the easy trip is not calm, and it is not natural. It is a very precise state of motion that only works because all the numbers line up. And then people make another mistake. They think that if getting into orbit is the hard part, then coming back must just be the reverse. It is not. Re-entry is not reverse launch. Re-entry is a controlled crash through the atmosphere. When a spacecraft comes back from orbit, it is still carrying enormous kinetic energy because it is still moving at orbital speed. That energy has to be removed somehow, And on Earth, the atmosphere does most of that job, but it does it violently. The vehicle hits thicker and thicker air, and motion turns into heat. A lot of heat. The spacecraft survives because the heat shield, the angle, the structure, and the timing all have to work together with very little room for error. If the angle is too steep, heating and stress rise fast. If the angle is too shallow, the spacecraft can skip off the atmosphere instead of descending properly. So when people talk about coming home from space like it's just landing, that hides what is really happening. The vehicle is surviving a very narrow corridor between bad outcomes. And there is something even more important here. Re-entry only works because Earth is still helping you. Earth gives you gravity strong enough to pull you back. Earth gives you an atmosphere thick enough to slow you down. Earth gives you oceans, land, recovery teams, tracking networks, hospitals, engineers, and an entire civilization ready to receive you. That is why a return from orbit is possible. It is not because space travel is reversible, it is because Earth is still doing most of the support work. So now the real pressure starts building. What happens when you go farther out and those supports begin to disappear? The farther you go, the weaker the assumption of return becomes. You are farther from rescue, you depend more on exact timing. You need more speed changes, which means more propellant. You spend longer outside the environment your body expects, and when something goes wrong, there are fewer ways to recover. Space does not become slightly harder with distance. It becomes harder in multiple ways at once. More energy, more delay, more exposure, more system risk, more dependence on machines. And this is where the main argument of the video becomes clear. When you hear the line, "People who leave Earth never come back," that does not only mean death. It does not only mean mission failure, it means something broader and more serious. The moment you leave Earth, you are no longer fully inside the conditions that made you human in the first place. Even if you physically land again, a lot has already changed. Your body has spent time outside its normal environment. Your survival depended on artificial systems instead of a living planet. Your return depended on a narrow set of physical conditions, not on a built-in promise. And that means back is already less solid than it sounds. That is why the word return is misleading. It makes space sound like a difficult version of normal travel. It is not. Space is a place where every part of your survival has to be rebuilt artificially, where speed is more important than distance, where coming home is not guaranteed by the route, and where Earth is not just your origin point, it is the only reason you are able to survive long enough to try. So before we even get to the moon or Mars or deep space, the comforting version of the story is already gone. Space travel is not naturally a round trip. Earth is not just where you started. Orbit is not safe in the ordinary sense. Re-entry is not simple. And once you leave, return becomes a temporary opening, not a promise. And if just getting away from Earth changes the rules this much, then what does it really mean to escape Earth's gravity completely? Escaping Earth is not normal travel, it's breaking out of a gravity prison. That sounds dramatic, but it is also just physically true. Most people think the hard part of spaceflight is going far away, like distance is the main problem. It is not. The first real problem is getting free. Earth holds onto you much harder than your instincts can understand, because your instincts were built for walking, driving, climbing, maybe flying in an airplane, not for escaping a planet. Earth's escape velocity is about 11.2 kilometers per second, or about 25,000 miles per hour. That is not the speed to reach the edge of the atmosphere. That is not the speed to get a nice view of Earth. That is the speed you need if you want to leave Earth's gravitational grip without needing more propulsion after that. And those numbers are so extreme that they barely feel real. A champion racehorse might run around 70 kilometers per hour, about 43 miles per hour. Escape velocity is around 160 times faster than that. So when people casually say, "we'll just go," they are talking about escaping a planet at a speed that has almost nothing to do with normal human experience. That is why your intuition fails here. Your brain understands hills, it understands effort, weight, slope, height. It does not understand gravity wells. Earth is not just a big rock sitting in space. It is a deep energy trap. The deeper you are in that trap, the more speed you need to get out. And that is why getting to space is not like crossing an ocean. It is more like trying to launch yourself out of a pit so deep that every extra bit of escape energy becomes brutally expensive. And here is where most people picture the whole thing wrong. They imagine rockets fighting height first, like the goal is simply to go up. But rockets do not fight distance first, they fight velocity. Yes, a rocket climbs. Yes, it rises through the atmosphere, but that upward motion is only part of the job. The real price is speed, especially sideways speed. To orbit Earth, you do not just go high enough to be in space, you go fast enough that while you are falling, the planet curves away beneath you. That is why orbit works. Height is just the setup. Velocity is the thing you are really paying for. This is one of the biggest mental corrections people need to make. Space is not up there in the simple way it feels. If you went straight up and did not build enough sideways speed, you would come back down. You might reach space technically, but you would not stay there. So a rocket is not mainly a tower climber, it is a speed machine. It is a vehicle built to dump enormous amounts of propellant in order to push a much smaller payload to extreme velocity. That is why launch vehicles look the way they do. They are mostly fuel. Most of the rocket is not crew, not cargo, not science equipment, not comfort, not safety margin. Most of it is propellant, because speed is expensive. And the really hard part is that the rocket has to carry that propellant while burning propellant to lift itself and the remaining propellant. That is the trap. The machine needs mass to gain speed, but mass is exactly what makes gaining speed harder. And that leads straight into one of the harshest facts in all of engineering: the math of rockets punishes ambition. The rocket equation is one of those ideas that sounds simple until you realize how much it controls everything. In plain language, here is what it means. If you want a spacecraft to change its speed by a bigger amount, you need more propellant. That propellant has mass. So to carry that extra propellant, you need even more propellant. Then that adds even more mass, which means you need even more propellant again. This is why round trips become so ugly so fast. The return fuel is not just return fuel, it is mass that had to be launched in the first place. And the fuel for that fuel is also mass. Then the tanks holding it add mass. The engines sized for it add mass. The structure needed to support it adds mass. Very quickly, the idea of just bring enough fuel to come back turns into a cascade of penalties that make the whole mission bigger, heavier, more expensive, and more fragile. So when people talk about missions beyond Earth like they are planning a long drive, they are missing the central problem. You're not planning a route, you're fighting arithmetic. Every kilogram you want later becomes a penalty now. Every hope for an easy return has to survive this brutal compounding effect. That is why so many mission designs look elegant in conversation and ugly in real engineering. Physics keeps sending the bill. So then people point to Apollo and say, fine, but we already left Earth, landed somewhere else and came back. So clearly this can be done. Yes, it can be done, but Apollo worked partly because the moon is close by cosmic standards. The moon is about 384,400 kilometers away on average, roughly 238,900 miles. For human life, that is an enormous distance. For the solar system, it is almost next door. That difference matters. Apollo succeeded because the target was relatively close, the mission duration was short and the crew could complete the whole chain. Leave Earth, travel, land, launch again, return before too many things had time to stack up against them. That stack matters more than people think. The longer a mission lasts, the more exposure you have to radiation, mechanical failure, navigation errors, health decline, fatigue, isolation, and simple bad luck. Apollo kept the timeline short enough that the system could survive its own complexity. Stretch that same basic architecture outward to Mars or an asteroid or anything deeper into the solar system, and the margin starts shrinking very fast. That is the real lesson of Apollo. It did not prove round-trip space travel is easy. It proved that with huge national effort, extreme risk acceptance, and a destination that is very close on a cosmic scale, a narrow kind of return was possible. That is a much less comforting lesson than people usually take from it. And all of this points to the biggest asymmetry in spaceflight. Leaving Earth is easier than rebuilding Earth somewhere else. Earth gives you gravity, pressure, breathable air, liquid water, ecosystems, magnetic shielding, huge temperature stability compared to space, and a full industrial civilization already running under your feet. It gives you all of that continuously, automatically, every second, and you do not have to launch any of it. Space gives you vacuum, radiation, thermal extremes, isolation, communication delay, and total dependence on machines. So every meter you move away from Earth increases the amount of Earth you have to carry with you or recreate artificially. Air, water, shelter, shielding, medicine, waste recycling, power, spare parts, guidance, navigation, food, and eventually even gravity substitutes or countermeasures. This is the trap most people do not fully see. The farther you go, the less you're just travelling, and the more you are dragging a shrinking copy of Earth behind you. And sooner or later, that changes the meaning of return. Coming back is no longer just a path on a map. It becomes dependence on a planet that still has to be reachable, still has to be functioning, and still has to be able to support you when you arrive. That is a much weaker promise than people think. So the hard truth is this: escaping Earth is not the beginning of easy movement through space. It is the first proof that space is hostile to return from the start. You're not leaving a city. You're trying to break free from a planet that gives you everything, using machines that burn themselves down just to buy enough speed to get a small piece of you out. And if escaping Earth already cost this much, then what happens when you make it to orbit and realise you are already becoming physically less suited to the planet you came from? Orbit sounds close to Earth, but the second you get there, normal human life is already over. That is the next thing people do not fully understand. They hear low Earth orbit and think near, safe, manageable. And in one sense it is near. The International Space Station is only about 400 kilometres, around 250 miles above Earth. That is much closer than most people emotionally picture. But biologically, orbit is not nearby life. It is alien life. The moment you reach orbit, you are no longer living in the conditions your body was built for. Astronauts on the ISS live in continuous freefall. They float because they are constantly falling around Earth, fast enough to keep missing the ground. That floating looks calm from the outside, but to the body it is a total environmental shock. On Earth, your bones and muscles are always working against 1G, even when you think you are resting. Standing, walking, lifting your head, keeping posture, all of it depends on gravity loading the body every second. In orbit, that load is gone, and when the load disappears, the body does not keep maintaining Earth-level strength out of loyalty. It starts adapting to the new conditions. That is the first hard truth of orbit. Your body is efficient, not sentimental. If gravity is no longer forcing you to carry weight, then the body starts acting like strength is optional. That adaptation helps in orbit, because you do not need the same muscle power or the same heavy skeleton when everything floats. But the exact same adaptation becomes damaged the second you think about coming back to a planet. And the changes do not wait around politely. They start almost immediately. Within days in microgravity, fluids begin shifting upward toward the head because gravity is no longer pulling them downward the way it does on Earth. Faces get puffy, legs look thinner. Astronauts sometimes call it having a puffy face and bird legs, because the whole fluid distribution of the body starts getting rearranged. That alone should tell you something important. Even before long-term damage, your body is already saying this is not the environment I expected. Then the inner ear gets involved. Your vestibular system, the system that helps you sense balance and emotion, was built under gravity too. In orbit, it gets confused. That is one reason motion sickness can hit fast in the first days of a mission. Your senses do not agree with each other anymore. Your eyes see one thing, your inner ear feels another, and your brain has to rebuild its sense of orientation from scratch. And then the bigger problems begin stacking up. Over weeks and months, muscle atrophy becomes serious, especially in the legs, back, and core, the parts of the body that normally fight gravity all day on Earth. Bone loss is even more disturbing. In some weight-bearing regions, astronauts can lose around 1% to 1.5% of bone mineral density per month without aggressive countermeasures. That is an extreme pace. On Earth, age-related bone loss usually happens slowly over years. In orbit, the body can start stripping out the architecture needed for life on a planet in a matter of months. That is why space exercise is not some nice health habit. It is damage control. Astronauts spend major amounts of time exercising because if they do not, the body starts drifting away from Earth's normal function faster than most people realise. And even with exercise, the problem is not erased. It is managed partly for as long as possible. So here is the next pressure point. If orbit can weaken your bones and muscles that fast, is that just discomfort? Or is something deeper going on? This is deeper. Space does not just make you uncomfortable, it starts rewriting your anatomy. NASA has documented a condition called spaceflight-associated neuroocular syndrome. The name sounds technical, but the meaning is simple and serious. Long-duration spaceflight can change the shape of the eye, flatten the back of the eyeball and affect vision. This is not just tired eyes or temporary blur. It is evidence that the body's pressure systems and fluid balance assume gravity exists. Remove gravity long enough and the internal layout of the body starts shifting in ways that can affect how you see. That should reset the whole conversation. Once vision changes show up, you are no longer talking about a person who is simply coping with an uncomfortable trip. You are looking at a body that is being physically remodeled by a non-Earth environment. The pressure relationships inside the skull, the movement of fluids, the structure of delicate tissues, all of it starts moving away from the conditions it evolved for. And this matters because people often picture astronauts as humans in their purest, toughest form, like they are proving the body can handle space. In reality, astronauts prove the opposite. They prove that even highly trained, medically screened, heavily supported humans can start changing when Earth's conditions are removed. Orbit is not showing that the body is universal. Orbit is showing how narrow the human operating window really is. Then there is another misconception people carry, that once you are in orbit, you are somehow independent. You are not independent. The station survives because Earth keeps feeding it. Food does not magically appear on the ISS. Oxygen systems do not maintain themselves forever. Water recovery hardware wears out. Spare parts fail. Filters clog. Electronics degrade. Scientific equipment needs replacement. Resupply vehicles bring cargo, fuel, experiments, maintenance hardware and basic necessities. Ground teams on Earth monitor the station continuously, helping with operations, troubleshooting, planning and safety. Even the orbit itself is not permanent. The station experiences drag from the thin upper atmosphere, so its orbit decays and has to be periodically boosted. That detail is important. Even at just 400 kilometers, around 250 miles above Earth, survival is not happening because orbit is naturally livable. Survival is happening because a huge industrial civilization below is constantly doing invisible work. Factories, launch systems, mission control engineers, software teams, tracking networks, medical experts, logistics chains, all of that is part of what keeps the station alive. So when people look at orbit and see independence, they are seeing the surface of the picture, not the full system. Orbit only looks self-contained because Earth is carrying so much of the load that you stop noticing it. And that brings us to the first really damaging conclusion in the whole argument. If low Earth orbit already changes the human body, even under constant support, with rapid communication, with continuous resupply and with a relatively fast emergency return option, then the idea of going much farther and coming back unchanged is not realistic. That fantasy breaks right here in near-Earth orbit. You do not need to go to Mars to prove the human body starts uncoupling from Earth. You do not need to go into deep space to show that life away from Earth comes with biological costs. Orbit already proves it, and orbit is the easiest serious version of space living we have. That is what makes this section so important. Orbit is not practice for Earth. Orbit is your first evidence that leaving Earth begins to turn you into something less perfectly matched to Earth. Not in a dramatic movie way, but in the quieter, more serious way that matters more. Your bones, your muscles, your circulation, your balance, your eyes, your daily function, all start adjusting to a place that is not a planet. So by the time people say, "We'll just go farther later," they are already skipping past the warning sign. The warning sign is orbit itself. It is telling you that space does not wait to become dangerous. The process starts as soon as normal gravity stops. And if the body starts coming apart from Earth this early, then the next question gets worse. Because now we have to ask what happens when you look at the human body directly and admit it was designed for one planet only. Your body is not built for space, it is built for one planet, and that planet is Earth. That is the next thing this idea forces you to face, dear. People talk about humans like we are flexible enough to live anywhere if the technology is good enough. But biologically, that is not true, at least not in any simple sense. Human beings are not general purpose life. We are a very specific kind of life, shaped by one gravity level, one pressure range, one temperature range, one food system, one atmosphere, one magnetic shield, and one day-night cycle. That is the operating window that built you. Your blood pressure system assumes Earth, your posture assumes Earth, your balance system assumes Earth, your sleep schedule assumes Earth, your immune system, your metabolism, your whole daily function assumes Earth. So space is not just dangerous because it attacks you from the outside with vacuum and radiation. Space is dangerous because the moment you leave Earth, it starts exposing how specialized you already are. That is why this problem is deeper than people think. It is not just that the environment out there is harsh. It is that the environment in here, inside your body, was calibrated for one world only. And once that calibration stops matching the place you are in, the body does not stay stable out of habit. It starts changing. Bone and muscle are the obvious example, but they're only the beginning. In microgravity, the legs, back, and core take the biggest hit because on Earth, those systems are constantly working against body weight. Even when you are just standing still, those muscles are active. They hold posture, support movement, and keep you upright under 1G. In orbit, that daily demand is mostly gone, so the body starts cutting back. Muscle wasting begins because from the body's point of view, maintaining all that strength no longer makes sense. Resistance exercise helps, but it does not fully erase the problem. It slows the decline. It fights back, but it does not turn orbit into Earth. That difference matters because people often hear about exercise systems in space and assume the problem is solved. It is not solved, it is managed, and only partly. Bone loss is even more serious. Bone is living tissue, constantly being broken down and rebuilt. On Earth, weight-bearing activity helps signal that the skeleton needs to stay strong. In space, that signal weakens. The body starts acting like carrying a dense, heavy skeleton is no longer a good investment. And that means the body begins dismantling the very structure you need to stand, walk, and live normally on Earth. That is the brutal logic of space adaptation. The body is not trying to protect your future return to Earth. It is trying to optimize for the environment you're in right now. And if that environment says heavy bones and powerful anti-gravity muscles are unnecessary, then the body starts stripping them away. So then the next question gets more serious, because if muscles and bones are changing, what about systems you cannot train as directly? The heart and circulation stop behaving like Earth systems too. On Earth, gravity pulls blood downward, so the cardiovascular system works continuously to move blood upward and maintain stable pressure when you stand, walk, or change position. In weightlessness, that demand drops. Blood and fluid redistribute differently, and over time plasma volume can decrease. The heart itself can become deconditioned and, because it is no longer working under normal Earth load conditions, then you come back to gravity, and suddenly upright posture is hard again. Standing can become difficult. Some astronauts experience orthostatic intolerance, which basically means the body struggles to handle being vertical. Blood pressure control is not responding the way it should. You stand up and the system is not fully ready for it. That should completely change how people think about coming home. Earth is not just a neutral place waiting for you to step back onto it. After enough time away, Earth becomes a challenge your body has to relearn. gravity becomes a test. Something that used to be automatic becomes stressful. And that matters for the main argument of the video, because it means return is not just a navigation problem or an engineering problem, it is also a physiological problem. You do not simply arrive and resume life. Your body may have to fight its way back into the conditions it originally evolved for. And then there is the system people forget even faster than circulation, the immune system. Spaceflight studies have shown immune dysregulation, changes in stress hormones, altered inflammatory responses, and even reactivation of latent viruses. In other words, the immune system does not stay normal in space. It shifts, and not in a reassuring way. Some parts may weaken, some responses may become less predictable, and some dormant biological threats inside the body may wake back up under the strain of the environment. That is already bad enough on a short mission near Earth. But a spacecraft is also a closed environment, and closed environments change microbial behavior too. The human body does not travel alone. You carry bacteria, fungi, and all kinds of tiny biological systems with you. In a sealed habitat, those systems interact with stress, recycling, air circulation, surfaces, and confined living conditions in ways that can become hard to predict. So now the danger is not just one big outside threat. It is a whole chain of uncertainty inside the body and inside the habitat. And the farther you get from Earth, the worse that uncertainty becomes, because you lose the things that make medical problems survivable on Earth. You lose rapid evacuation, you lose hospitals, you lose specialists, you lose imaging systems, operating rooms, blood banks, large pharmaceutical support, and massive medical infrastructure. That is a key shift. On Earth, medicine works partly because civilization is huge. In deep space, medicine has to fit inside the mission, and that means every unresolved biological risk becomes much more dangerous. Not because it is guaranteed to happen, but because if it does happen, you're trapped with fewer options. And then the final question in this section is the one that raises the stakes the most. Can humans actually live through full life cycles off Earth? Right now, we do not really know. We do not have solid evidence that humans can safely conceive, gestate, develop, be born, grow, and mature through full life cycles in low gravity, partial gravity, or high radiation deep space conditions. That is not a small missing detail. That is the core requirement for any real off-world civilization. If a species cannot reliably develop away from its home planet, then it has not actually expanded in a lasting way. It has only sent out temporary expeditions. That means every mission, no matter how advanced, is still leaning on Earth as the source of the next generation, the stable biology, the original baseline. This is where the whole argument gets much bigger than one astronaut or one mission. Because now return is not just personal, it becomes civilizational. If humans cannot sustain multi-generational life off Earth, then every person who leaves is still part of a chain that ultimately depends on coming back, or being replaced by someone who came from here. And if that dependency never breaks, then humanity has not really escaped Earth at all. It has only learned how to send temporary human presence into hostile places. That is why this section matters so much. It is not just saying space is hard on the body, it is saying the body itself is evidence that Earth is not optional for humans in the way people like to pretend. Every major system inside you carries the signature of one planet. Bones, muscles, circulation, immunity, sleep, balance, development, all of it points back to Earth. So when people say humans are meant to become a spacefaring species, the real question is not whether we can visit space, we already can. The real question is whether the human body as it exists now can stop being an Earth body and remain fully human in the same way. And so far, the evidence points in a much darker direction. Because if your own biology is this dependent on Earth, then the next thing waiting for you outside that dependence is even worse. Radiation, the invisible force that does not just stress the body, it quietly starts trying to unmake it. Radiation is one of the clearest reasons space is not just dangerous, it is actively hostile to human biology. A lot of people think of space as empty, cold and soilent, That picture is incomplete. Space is also full of radiation, and most of the time you do not feel how much Earth protects you from it. Down here, you are living under layers of protection that work so well you can go your whole life without noticing them. The atmosphere absorbs and scatters a huge amount of harmful radiation. The magnetosphere helps deflect charged particles that would otherwise hit much harder. Together, those systems act like a shield around everyday human life. That shield is so normal that people stop seeing it. But the second you move beyond it, especially beyond low Earth orbit, the environment changes fast. You enter a much harsher region filled with galactic cosmic rays and solar energetic particles. So space is not empty in the way people imagine. It is full of invisible damage, and the farther you go from Earth, the less protected you are from it. That is the first correction people need to make. Radiation in space is not some side issue sitting in the background. It is one of the main reasons long-duration missions become so difficult. It is not just another discomfort you manage with better design. It is one of the things trying to break the human body at the deepest level. And that brings up the next misunderstanding, because a lot of people hear the word radiation and think of medical scans. Deep space radiation is not like getting an X-ray. A medical X-ray is controlled, brief, and targeted. It is used in a setting where the dose is managed, the exposure is limited, and the risk is accepted because the benefit is immediate. That is not what deep space radiation looks like. In deep space, you are dealing with high-energy particles that can pass through tissue, damage DNA, increase cancer risk, and potentially affect the central nervous system. This is not a neat little exposure event that starts and stops when the scan is over. It is a background hazard that follows you for the entire mission. That difference matters because it changes how you think about mission duration. The longer you are out there, the more exposure accumulates. And unlike some engineering risks, this is not always a problem you can fully seal away with a thicker wall and move on. The particles involved can be extremely penetrating. So radiation becomes a design limit, a health limit, and a mission planning limit all at once. This is why NASA and other space agencies treat radiation as one of the major barriers to long-duration human missions, not as a dramatic talking point, not as speculative fear, but as a real planning constraint. It shapes spacecraft design, transit timing, operational risk, and medical limits. That is important to say clearly because people often treat radiation concerns like overcautious pessimism. They are not. They are part of the actual reality of sending humans beyond Earth's protective zone. So now the situation gets even worse because some radiation is not just steady exposure over time. Some of it can hit hard and fast. Solar storms can turn a difficult mission into a lethal one. The sun does not just shine, it also produces violent events that can throw out large numbers of energetic particles. A major solar particle event can deliver dangerous radiation doses over short timescales. That means a crew in deep space cannot just think in terms of average exposure over months. They also have to think about sudden spikes that can become serious very quickly. This is where shielding strategy becomes critical. A spacecraft may need a storm shelter area, extra shielding around certain compartments, forecasting support and mission timing designed to lower risk as much as possible. Earth protects you from this by default. The atmosphere and magnetosphere handle most of that problem automatically. In deep space, nothing handles it automatically. You have to engineer the protection yourself, and your engineering has mass limits, design limits, and failure limits. That is a major theme in this whole video. On Earth, survival is the default and technology extends your options. In deep space, danger is the default and technology is just trying to hold the line. If a strong enough solar event hits and your shielding is not good enough, your return problem may be finished before the return window even arrives. The mission may still be technically flying, but the people inside it may already be carrying damage that changes everything. And then people make another mistake. They assume that if you can just reach Mars and get onto the surface, you're finally safer because at least you are standing on ground. Mars is not safe just because it has ground under your feet. Mars has an atmosphere, but it is extremely thin, around 6 millibars on average surface pressure, which is less than 1% of Earth's sea level pressure. That is not enough to give you Earth-like shielding. Mars also does not have a global magnetic field like Earth's. So while being on the Martian surface can reduce some exposure compared with being in open deep space, it does not solve the problem in anything like an Earth-level way. That means long-term living on Mars likely requires serious shielding measures. You're not just building a habitat with walls and windows and calling it a colony. You're probably burying habitats under regolith, covering living spaces with local material, or building substantial shielding into the structure from the start. And that should tell you something important. Even after arrival, you're still inside the same basic trap. You're still trying to recreate a piece of Earth badly enough to keep human biology from being slowly damaged. So reaching another world does not mean you have escaped the problem. It means you have arrived at a place where the problem continues in a slightly different form. Mars is not a safe second Earth waiting for settlers. It is a hostile environment where survival still depends on layers of artificial protection, and radiation remains one of the main reasons why. And that leads to the hardest point in this whole section. Radiation does not just threaten comfort, or mission success, or lifespan in some abstract future sense. It threatens the integrity of the body itself. This is what breaks the simple frontier story people like to tell. Space is not an open landscape waiting for tough humans to move in. It is an environment that can continuously damage the molecular instructions that keep your cells working properly. That is a much deeper problem than most popular space talk admits. You're not just worrying about accidents or equipment failure. You're worrying about the environment steadily working against the code your body runs on. And once that is true, the meaning of coming back changes again. Now it is not just about whether the spacecraft makes it home, whether the fuel margins work out, or whether the launch windows line up. It is also about whether the person trying to come back is still biologically stable enough to survive what comes next. That is why radiation is such a powerful part of this argument. It shows that space does not need to kill you dramatically to separate you from Earth. It can do it slowly, invisibly, and continuously. It can do it while the mission looks successful from the outside. It can do it while the crew is still working, still communicating, still moving toward the next milestone. The damage does not need to announce itself in a cinematic way to matter. It only needs to accumulate. So by this point, the picture is getting much darker. Earth is not just your home world, it is your shield. Beyond that shield, space begins attacking the body at the level of tissue, DNA, and long-term function. Even landing on another planet does not remove the threat. It just changes the way you try to manage it. And if the environment is this hostile to your body, even when the mission itself is still functioning, then the next question becomes brutally practical, because now we have to ask what happens when something goes wrong and you need help. But distance has already turned rescue into a fantasy. Distance does not just make space harder, it makes rescue stop meaning what you think it means. On Earth, rescue feels normal because Earth is packed with infrastructure. If a jet has a problem, there are airports, runways, radar, weather tracking, coastguards, military assets, rescue helicopters, hospitals, fuel networks, mechanics, and entire governments that can respond. Even when rescue is difficult, the system exists. The planet is covered in options. That is why people casually assume help is always part of the background. But once you move off Earth, that background starts disappearing fast. In orbit, rescue is already difficult. In cislunar space, it gets slower and more limited. At Mars distance, rescue is nearly meaningless. There is no Coast Guard in interplanetary space. There are no roadside mechanics. There is no ambulance that can launch, catch up, fix the problem, and bring you back. That idea only works in human life because Earth is dense with tools, people, fuel, medicine, and infrastructure. Space has none of that unless you brought it with you first. That is the first thing distance destroys. It destroys the assumption that somebody else can step in, and the numbers get brutal very fast. The moon is close enough that a mission there is usually measured in days. That is still serious, but it is within a timescale where rescue, contingency planning, and short-term survival can at least be discussed in a meaningful way. Mars is a different category completely. Using current propulsion, one-way transit to Mars is roughly 6 to 9 months depending on the mission profile and orbital alignment. That alone should reset the way people think about it. If something goes wrong on the way to Mars, you're not waiting for help over the weekend. You're trapped in a system where even reaching the destination takes most of a year. And that is only one part of the trap, because Mars and Earth are not fixed at one distance from each other. Their separation changes enormously as they move around the Sun. At a favourable close approach, Mars can be roughly 54.6 million kilometres away, about 33.9 million miles. When the two planets are on opposite sides of the Sun, that distance can climb to well over 400 million kilometres, more than 248 million miles. That means Mars distance is not one simple number. Sometimes it is bad, sometimes it is much worse. And rescue plans have to live inside that reality, not inside the cleaner version people imagine when they hear a single average distance. So now the next hard point becomes unavoidable, because if distance changes that much, then coming home cannot just be about deciding when you feel ready. Return windows are orbital, not emotional. This is one of the most important things people fail to feel. In deep space, you do not come home when you want. You come home when celestial mechanics allows an efficient transfer. The planets have to be in the right places. Your vehicle has to have enough propellant. Your systems have to still work. Your crew has to still be functional enough to execute the return. If any of those conditions fail, then wanting to go home changes nothing. That is why missing a window is not like missing a flight. If you lose propellant margin, damage a major system, arrive in worse health than expected, or fail to launch on time from the surface of another world, the chance to return may slide away for months or longer. In deep space, timing is not a convenience. It is a rule enforced by orbital mechanics. You do not negotiate with it. You live inside it or you lose. And this matters because people still carry the Earth habit of thinking that urgency creates solutions. On Earth, if something is serious enough, you can usually throw more resources at it. Faster transport, emergency procedures, more staff, more equipment. In deep space, urgency does not change the positions of planets. The sky does not care how badly you want a rescue. Then there is another illusion that collapses once distance grows, the idea that Earth can still guide everything in real time. Communication delay destroys that fantasy. The Moon is about 1.3 light seconds away. That is short enough that communication still feels fairly immediate, even though it is not perfectly instant. Mars is completely different. Depending on where Earth and Mars are in their orbits, the one-way delay can range from about 4 light minutes to more than 20 light minutes. That means a back and forth exchange can take 8 to over 40 minutes round trip. That delay changes the entire logic of support. You cannot do real-time troubleshooting with the same fluid pace as mission control helping a crew in low orbit. You cannot remotely pilot delicate operations the way people imagine in movies. You cannot do real-time surgery guidance in the ordinary sense, where a doctor responds instantly to changing conditions. Even basic problem-solving becomes slower, more fragmented, and more dependent on local judgment. So deep space crews are not just farther away physically, they are functionally on their own. Earth can still send advice, procedures, analysis, and planning support, but it cannot be present in the moment the way it is for near-Earth operations. That is a huge shift, because it means every emergency becomes more local the farther out you go. And once that is true, the final point of this section gets very sharp. At scale, return stops being Earth's solution and becomes your local problem. The farther you go, the less Earth can intervene in any practical way. Your habitat has to work where you are. Your power has to exist where you are. Your life support has to keep running where you are. Your spare parts, your medicine, your repair capacity, your radiation shelter, your ascent vehicle, your fuel, your ability to survive until the next launch opportunity. All of it has to already be there, or arrive in advance or be produced locally. Earth cannot keep solving these problems for you at the moment. You need help. That is the real transition people underestimate. You stop being a traveller and become a self-contained island. And islands in space do not get to assume ferries home. They survive by internal stability, stored margin, redundancy, and local capability. If those fail, Earth may know about it, Earth may care about it, Earth may even try to respond in some limited way, but caring is not the same thing as reaching you. This is why distance is more than a number. Distance changes the structure of survival. It changes rescue from an expectation into a fantasy. It changes Earth from an active support system into a distant reference point. It changes return from something backed by civilization into something that has to be built, maintained, and executed by the stranded system itself. And that is a much darker truth than people usually admit. Because the farther you go, the less meaningful it is to say help is available. If the trip takes months, if the windows are narrow, if the delay is long, if the systems on site are the only systems that can act in time, then Earth is no longer your solution. Earth is just where the signal comes from. So by this point, the trap is tightening in a very clear way. Your body changes when you leave Earth. Radiation keeps attacking you while you are gone, and distance strips away rescue until survival depends almost entirely on what is already with you. And once that happens, another kind of separation starts building too, one that is less obvious at first, but just as real, because even if your spacecraft holds together, time itself starts pulling you away from the world you thought you were going back to. Even if the spacecraft survives, time is still pulling you away from Earth the entire time you're gone. This is where the argument gets deeper, because now the problem is not only physics, biology, or distance. It is time. People usually think of return as a simple physical event. You leave, you travel, you land again, and that means you are back. But that is not how human life really works. Human life is not just location, it is timing. And the longer you're away from Earth, the more that timing breaks. You do not leave Earth's timeline and come back untouched. Human societies change fast. Technology changes. Economies change. Relationships change. Institutions change. Even the way people talk changes. A mission beyond Earth can last long enough that the world you return to is operating under different assumptions than the one you left. That sounds abstract until you think about how quickly whole eras can shift now. A few years can completely change the public mood, the tools people use, the balance of power, the meaning of security, even the basic background of daily life. So when people picture a crew coming home, they often picture a pause button, as if Earth just waits, as if the crew steps out of time, does something difficult, and then steps back into the same story. But there is no pause. Earth keeps moving the whole time, and that means return is already broken in another sense. You can come back to the same planet, but not to the same moment. That point gets even more interesting because people hear time in space and immediately think about relativity. Yes, relativity is real. Special and general relativity mean clocks tick differently depending on speed and gravity. GPS satellites already have to account for that. But in low orbit and ordinary human missions, the physical time differences are tiny. They are real, but they are not the main thing changing human life. The more important version, at least for missions anywhere near realistic human planning, is social relativity. That is the version that matters first. While you are away, everyone else keeps updating with the world in real time. New events happen, new systems replace old ones, new conflicts start, new alliances form, new software, new laws, new norms, new expectations. Families change, children grow up, parents age, friend groups shift, whole cultures move on. You are not just physically distant from Earth, you are increasingly out of sync with it. That is a major part of what this video is arguing. Coming back is not only about getting a body through re-entry, it is about whether you can rejoin a moving civilization after being separated from its normal pace. And the longer the mission, the less obvious that becomes. So then the next question gets sharper, because if Earth keeps changing while you are away, how extreme could that mismatch become? A Mars crew could come home to a different planet. A long Mars mission could span elections, wars, economic ration, scientific breakthroughs, AI disruption, public unrest, institutional collapse, or major shifts in global strategy. A mission might launch under one government, one policy, one public mood, one funding environment, and then return to something completely different. The people who sent you may no longer be in power, the priorities that justified the mission may no longer exist. The civilization you return to may still be there physically, but the structure around your mission may be transformed. That is why re-entry is not only atmospheric, it is historical. You do not rejoin where you left off. There is no bookmark in civilization waiting for you. The timeline keeps moving and rewriting the context of your mission while you're gone. So even a successful return can mean arriving into a country or a planet that understands your mission differently than it did at launch. And that matters psychologically too, because now you're not just dealing with distance and biology, you are dealing with belonging. Psychological return may be harder than physical return. Astronauts already report that spaceflight changes perspective, identity, and emotional attachment to Earth. Seeing the planet from outside changes how people think about conflict, fragility, and scale. That shift is real, even on shorter missions. Long-duration isolation adds another layer. Isolation changes cognition, stress, mood, conflict dynamics, and the way people attach meaning to routine. A crew deep in space will build its own habits, values, rhythms, and internal world simply because it has to. So when that crew comes back, the difficulty is not just that their muscles are weaker or their balance is off, it is that their minds may now be calibrated to a different way of living. Earth can feel loud, crowded, heavy, chaotic, and strangely unreal. The people back home have been living inside a stream of constant change, while the crew has been living inside a closed mission structure with a very different rhythm and purpose. That creates a painful mismatch. You may come back with memories nobody fully shares, with priorities that do not fit cleanly into ordinary life, and with a sense that the world kept moving without you, because it did. In that sense, you come back older in memory than in belonging. You have lived through something that separates your internal timeline from everyone else's. And then, the final point in this section makes the whole argument even bigger, because eventually this will stop being about crews and start being about communities. The first permanent off-world settlers will prove this point completely. Once humans live somewhere else for years or decades or generations, return stops looking like going home. It starts looking more like moving between worlds with different clocks, economies, institutions, and values. A settlement on the Moon, Mars, or anywhere farther out would not stay culturally identical to Earth forever, even if it started that way. Different delays, different risks, different living conditions, different local priorities, all of that would push it in its own direction. And once that happens, the meaning of being from Earth starts changing. The first humans who truly leave Earth may not be trapped mainly by propulsion. They may be trapped by history. Their lives, relationships, and institutions may become so adapted to where they are that going back is no longer simple, even if the engines exist. And that still counts as non-return, because home is not just coordinates, home is synchronization. It is being in step with a place, a culture, a time, and a way of life. Once that synchronization breaks, return becomes much less complete than it sounds. That is why this section matters so much to the overall argument. Up to now, the trap has been physical. Gravity, biology, radiation, rescue, distance. Now the trap becomes temporal. Time itself starts separating you from Earth. Not through science fiction tricks, but through the ordinary fact that civilization keeps changing while you are absent. The world does not hold still for astronauts. It does not hold still for settlers. It does not hold still for anyone. So even if the spacecraft works, even if the mission survives, even if the crew physically makes it back, there is now another problem waiting for them. They are trying to return not just across space, but across a gap in shared time. And if time can already pull you away this much before you even leave the inner neighbourhood of Earth, then the next step gets more serious. Because now we have to look at the Moon, the place that seems reachable, solved, and almost familiar, until you count what it actually takes to get there and come back. The Moon looks reachable, but that feeling starts breaking the second you count what return actually costs. Apollo made the Moon look solved, and that may have been one of the most misleading victories in space history. Apollo 11 landed in 1969, and in total 6 Apollo missions landed humans on the moon. Because it happened, and because it happened more than once, people started absorbing the wrong lesson. They started treating lunar return like a hard thing that became easy once humanity proved it could do it. That is not what Apollo proved. Apollo proved that with massive rockets, national-scale funding, huge industrial support, short mission timelines, and extreme acceptance of risk, humans could barely do it. That is a very different statement. The Saturn V was not a normal launch vehicle. It was a gigantic machine built to throw a very small number of humans toward a nearby world with very little room for failure. The missions were designed to be short because the longer they lasted, the more ways things could go wrong. And Apollo 13 showed exactly how thin the safety margin really was. One major failure, one damaged spacecraft, one chain of problems, and suddenly the whole idea of go there and come back turns into a survival crisis. That is why the moon is so useful for this argument. It is close enough to make people overconfident. It looks like proof that round-trip space travel is under control. But if you look at what it actually took, the opposite lesson appears. Lunar return was never casual. It was a tightly controlled high-risk operation that worked under specific conditions and almost failed catastrophically more than once. And then there is another misconception people carry over from that history. They think the moon must be gentler than orbit because at least it has gravity. Lunar gravity helps, but it does not save you. The moon's surface gravity is about 1.62 meters per second squared, roughly 1/6 of Earth's gravity. That changes a lot. It changes how you walk, how you jump, how dust moves, how tools behave, how landing works, how ascent works, and how vehicles have to be designed. It is not nothing, but it is also not Earth. And that difference matters more than people want it to. 1/6 gravity may reduce some of the worst effects of total weightlessness compared with living in orbit, but we still do not know if that level of gravity is enough to preserve long-term human health. That is the key unknown. Is partial gravity enough to maintain bones properly, muscles properly, circulation properly, development properly, over months, years, or generations? Right now, we do not know, and when you do not know the answer to a question that basic, you cannot honestly call the moon safe in any long-term human sense. That is a major point people skip over. They hear there is gravity there, and mentally slide straight to so the body will probably be okay. But probably is doing way too much work in that sentence. The moon may be less damaging than microgravity in some ways, but less damaging is not the same thing as biologically stable. The moon is still an environment where the human body is operating outside the conditions it evolved for. And then the moon adds another problem that sounds small until you realise it gets into everything. Lunar dust is a real engineering and medical problem. Apollo astronauts reported that lunar dust was abrasive, clingy, and irritating. It stuck to suits, it got into equipment, it caused trouble with seals, joints, and fabrics. It smelled strange when brought into the cabin, and it raised concerns about inhalation. This is not ordinary dust like dirt on Earth. The moon has no weather and no liquid water to smooth things out over time. Its regolith has been shaped for billions of years by micrometeorite impacts, which means many of the grains are sharp, jagged, and mechanically nasty. That matters because long-term lunar operations depend on hardware surviving repeated exposure. If dust gets into seals, bearings, connectors, filters, radiators, suit joints, optical surfaces, and habitat systems, then over time it becomes a slow destruction process. The moon is not just a cold desert. It is a place where the ground itself keeps trying to wear down your machinery, and that goes beyond engineering. If fine abrasive dust gets into lungs or living spaces, it becomes a human health issue too, so the moon is not a clean stepping stone waiting for human expansion. It is a place where even the dirt becomes part of the survival problem. That should seriously change how people talk about just building a base there. You're not setting up camp on a simple empty plain. You're trying to keep humans and machines alive in an environment that degrades both. So then the next question becomes unavoidable, because even if you accept the dust, the weak gravity, and the harsh environment, what does it actually take to bring someone back? Every kilogram returned from the moon costs absurd effort. People say come back from the moon like it is one step. It is not one step. To return, you need a lander that survives descent. You need systems that remain functional on the surface. You need an ascent stage that can launch off another world. You need enough fuel. You need guidance and navigation that still work. You need rendezvous and docking with a spacecraft still operating in lunar orbit. And then you need the return vehicle itself to stay alive long enough to get everyone back to Earth safely. That whole chain has to hold together. Miss one part, and return disappears. The moon is only about 3 light seconds round trip for communication, so compared with Mars it feels close. But operationally it is still a separate world. The moment you land there, you are no longer doing one mission. You are doing a linked sequence of missions that all have to succeed. Landing is one mission, surface survival is another, launching off the moon is another, rendezvous is another, return transit is another, re-entry at Earth is another. That is why lunar return is so deceptive. It is near enough that people think it should be easy, but it is still far enough that every part of the return chain has to be built with huge care and very little tolerance for failure. In practice, bringing people back from the moon means rebuilding a mini space program on site every single time. And that brings us to the real lesson the moon teaches. The moon is close enough to tempt us, and harsh enough to expose the truth. That is why it matters so much. It is the nearest place where humanity can learn the same rule that will control the rest of the solar system. Once you leave Earth, survival depends on carrying a shrinking copy of Earth with you. Air, water, shelter, pressure, power, medicine, waste handling, navigation, repair capacity, communication, all of it has to come along in some form. The moon does not remove that rule. It teaches it. Yes, return from the moon is possible, history proves that. But even there, return is never casual, never guaranteed, and never cheap. It depends on precision, layers of hardware, huge support structures, and short timelines that keep risk from piling up too far. And if that is true for the nearest major destination beyond Earth, then the lesson for farther missions gets darker very quickly. So the moon is not proof that return is easy. It is proof that even the most reachable off-world destination still turns coming home into a complex, fragile chain of success conditions. It looks close, but the price of proving that closeness is huge. And once you fully understand that, the next destination becomes much more serious. Because if the moon is already this demanding, then Mars is where the comforting idea of coming back really starts to break. Mars is where the idea of coming back stops sounding hard and starts sounding unstable. That is why Mars matters so much in human imagination. It is not just another target, it is the planet that seduces almost every space dream. Mars has a day length close to Earth, about 24 hours and 39 minutes. It has seasons, it has polar caps, it has weather, it has giant canyons, giant volcanoes, and strong evidence that liquid water existed there long ago. Out of all the places people talk about, Mars is the one that most easily feels like a second chance at planetary life. And that is exactly what makes it dangerous, because it looks almost habitable. People relax too early. They see familiar features and start mentally editing out the deadly parts. A sky, a horizon, a day-night cycle, dust storms, frozen water. These things make Mars feel like a harsh version of somewhere we could manage. But almost is doing a huge amount of work there. Mars is not almost Earth in the way that matters for survival. It is still a lethal world. It only feels emotionally closer because it has some of the right shapes. That is why Mars is the most misleading destination in the solar system. It looks like a place where humans could live with effort. And maybe someday they can. But that visual familiarity hides how fragile that life would be, how dependent it would be on machines, and how easily the path home starts falling apart. And the first place that illusion breaks is the atmosphere. Mars's atmosphere is too thin to live in and too thick to ignore. It is mostly carbon dioxide, and it is extremely thin. You cannot breathe it. You cannot walk outside in it. It does not give you Earth-like pressure, Earth-like warmth, or Earth-like protection. But even though it is thin, it is not absent. That is what makes Mars especially difficult. The atmosphere is thick enough to create serious entry, descent, and landing problems, but not thick enough to make those problems easy to solve. That sounds technical, but the basic idea is simple. On an airless world, you handle landing one way. On a thick atmosphere world, you handle it another way. Mars gives you the awkward middle case. There is enough atmosphere that you slam into it during entry and have to manage heat and drag, but not enough atmosphere to slow large human-class payloads down efficiently by itself. So you cannot ignore the air, but you also cannot count on it enough. That is one reason landing heavy payloads on Mars remains one of the hardest unsolved problems in practical human exploration. Sending robots is hard enough. Sending large habitats, ascent vehicles, life support systems, surface power, supplies, fuel equipment, and humans safely to the surface is in another class entirely. And that matters because every kilogram you need for survival and return has to get through that landing phase first. So Mars is already attacking the idea of return before you even touch the ground. If landing the hardware is hard, then surviving long enough to use that hardware becomes even harder. Then there is the next dangerous maybe. Mars gravity may be enough to hurt you and not enough to save you. Mars gravity is about 3.71 meters per second squared, around 38% of Earth gravity. That is much better than microgravity if you're thinking in simple terms. You will not be floating all the time. You can walk. You can work on the surface. You can use your body in ways that look more like life on a planet. But the problem is that better than microgravity does not automatically mean good enough for human life over the long term. That is the uncertainty people often glide past. Is 38% of Earth gravity enough to preserve bones? Enough to preserve muscles? Enough for healthy circulation? Enough for pregnancy? Enough for child development? Enough for multi-generational life? We do not know. And until you know, Mars remains biologically questionable in a very serious way. That is why Mars may be one of the worst environments from a human point of view. It may be survivable enough to encourage staying, but hostile enough to slowly damage the people who stay there. That is a nasty combination. An environment that kills you instantly is brutal, but at least it is clear. An environment that lets you function while gradually wearing down your body is more dangerous in a long-term civilization sense because it creates commitment before it gives you certainty. So by now, the core trap is becoming obvious. Mars is not just a harder moon. It is a place where multiple unresolved problems pile up at the same time, and all of them affect the chance of coming home. And then you hit the part that really breaks the fantasy. A return mission from Mars needs a second launch from another planet. This is where people finally start to see how serious the phrase coming back really is. To come home from Mars, you do not just survive the trip there. You do not just land. You do not just live on the surface for a while. You do not just wait for a ride home. You have to survive the transit, survive the radiation, survive the landing, survive the habitat, survive the dust, survive the psychological pressure, survive the medical uncertainty, and then, after all of that, you have to launch off Mars itself. That means the return is not one smooth continuation of the outbound mission. It is another planetary mission layered on top of the first one. Your ascent vehicle has to work. Your fuel has to be there. Your systems have to still be healthy enough. Your crew has to still be capable enough. Your departure timing has to still align. Your transfer system home has to still function. Returning from Mars is not flying back. It is successfully doing another major mission while already worn down by the first. That is a completely different picture from the way people casually talk about Mars settlement. It is not, we go there, build up and come back when we want. It is, if every major system survives long enough, and if the crew remains healthy enough, and if the local infrastructure still works, and if the orbital timing still cooperates, then maybe the second half of the overall mission can begin. That is not a small distinction. That is the whole distinction. And once you follow that logic to its end, the final point becomes very hard to ignore. The first Mars settlers may be functionally permanent even if no one says the word permanent out loud. Mission plans can include return. Engineers can design return architectures. But economics, logistics, health decline, and local infrastructure reality may still turn early Mars populations into one-way populations in practice. Not because the laws of physics make return totally impossible, but because real systems make it increasingly unlikely, increasingly delayed, increasingly expensive, or increasingly dependent on conditions that may not hold. That distinction matters. The universe does not need to physically lock the door if engineering, biology, and distance have already done the job for free. A return plan on paper is not the same thing as a robust return capability under real mission conditions. And the farther people spread across Mars, the more that gap could widen. Some may stay because they cannot safely leave. Some may stay because the infrastructure to leave is too limited. Some may stay because after enough time, health, adaptation, economics, and local dependency make return less realistic than staying put. That is why Mars is the point where the idea of coming back starts to break in a very public way. It is still close enough that people can imagine a round trip, but far enough that the round trip becomes a chain of survival problems with no guarantee of closure. It is close enough to inspire ambition and far enough to punish it. So the lesson of Mars is not that return is impossible in the strictest physical sense. The lesson is more unsettling than that. Return may remain technically imaginable while becoming practically fragile, biologically costly, economically weak, and operationally easy to lose. And once that happens, the difference between possible and not really happening starts shrinking fast. So if Mars already pushes return to the edge of practicality, then the next step is much worse. Because beyond Mars, the solar system stops looking like a set of destinations and starts looking like a one-way map. Beyond Mars, the solar system stops looking like a network of destinations and starts looking like a one-way map. That is the next major break in the story. Up to Mars, people can still trick themselves into thinking in familiar terms. Hard trip, dangerous landing, difficult return, but still inside the emotional range of mission out, mission back. Once you go beyond Mars, that framing starts collapsing. The distances get larger so fast and the support from Earth gets weaker so fast that the idea of return begins to lose practical meaning. Take the asteroid belt. Popular culture often shows it as a dense field of tumbling rocks packed close together, like a giant obstacle course. In reality, it's mostly empty space. The asteroids are spread far apart, so the belt is not dangerous because you're constantly dodging rocks like in a movie. But that does not make it easy for humans. It just means the real problem is not collision. The real problem is distance. Once you're pushing outward to the asteroid belt, travel times stretch, communication lags grow, life support has to run longer without failure, and the whole mission has more time to accumulate damage. That last point is critical. Even if nothing dramatic goes wrong, long missions create risks simply by continuing. More time means more wear on systems, more chances for parts to fail, more chances for the crew to get sick, more chances for small errors to become large ones. And there is another problem quietly getting worse at the same time. Solar power weakens as you move away from the sun. That means the farther out you go, the less useful one of your cleanest and most familiar energy sources becomes. So every mission deeper into the solar system has to become more robust, more autonomous, and more self-sustaining. That alone makes outbound travel feel more permanent. Not because anyone formally declares it one way, but because every extra month and every extra failure mode makes the return less secure. And then things get much harsher once people start talking about Jupiter and Saturn. Jupiter and Saturn are not destinations for humans in the normal sense. Their moons are scientifically extraordinary. Europa may have a subsurface ocean. Enceladus is one of the most interesting places in the solar system. Titan has a thick atmosphere and bizarre chemistry. These worlds matter a lot for science, but that scientific excitement can create another dangerous illusion, that these are just farther versions of Mars. They are not. The trip lengths alone become extreme, but the radiation environment around Jupiter is one of the biggest reasons the whole idea becomes so hostile. Jupiter's magnetosphere is enormous and violent. It traps intense radiation that can punish spacecraft and would be deeply dangerous for humans. So when people talk casually about sending humans to Europa, or deeper into the Jovian system, they are skipping over a major reality. This is not like exploring a distant desert or even another planet. You are entering one of the harshest radiation environments in the solar system. That is why the usual language of exploration starts failing out there. You're not visiting some rough frontier town. You're trying to survive inside the influence of a giant planet whose magnetic environment can act like a weapon against your machinery and your body. And even if you manage to get there, the challenge of staying alive and then coming back would be in a different category from anything humanity has done. Then there is the quiet systems problem that gets worse everywhere beyond Mars, not just around giant planets. The outer solar system dilutes sunlight, and with it a huge part of the support structure you take for granted. Sunlight does not just fade a little with distance, it drops with the square of distance from the sun. That means the change is steep. At Jupiter, sunlight is roughly 1/25th of what Earth gets. At Saturn, it is around 1/100th. That's a huge drop. And once sunlight falls that much, power generation, thermal control, agriculture and habitat design all become harder. This matters because the sun does much more for a human mission than simply provide light. It supports solar power. It affects temperature management. It shapes how practical surface operations and long-term outposts might be. Near Earth, the sun feels like a powerful nearby resource. Farther out, it starts behaving more like a distant lamp. Still there, still important, but much weaker as a direct support for human survival. That means every system has to work harder. If you want heat, power, food production, artificial light and stable habitat conditions, the burden shifts more heavily onto whatever machinery you brought with you. And once again, the farther you go, the more Earth has to be recreated locally just to keep a crew alive. So then the next consequence becomes unavoidable. Travel times in the outer solar system start stretching human life itself. Even robotic missions to the outer planets take years. Human missions, using anything close to current propulsion ideas, would become monumental multi-year commitments. That means you are not just planning a longer trip. You're planning a long period of accumulated exposure to everything that has already been building in this video. More radiation over more time, more chances for hardware to degrade, more medical uncertainty, more psychological pressure, more supply dependency, more opportunities for one unnoticed weakness to become mission-ending. That is why in very long missions, return stops feeling like a clean second phase. It becomes just the last fragile phase of one continuous decline curve. That phrase matters. Return is not a fresh event starting from a stable baseline. By the time you are trying to come home from deep in the solar system, the crew and the vehicle have already spent years being stressed, worn down, and tested. So the return is attempted not by a pristine system, but by a system already carrying accumulated damage. That is a much darker picture than most people naturally imagine. They think of outbound and inbound as two equal halves of a mission. In reality, the inbound part may be attempted by the weakest version of the mission, after most of the time wear, exposure and strain have already happened. And once you understand that, the final point in this section becomes very hard to avoid. At some distance, leaving Earth becomes functionally the same as exile. Not because anyone officially declares it one way, not because the laws of physics say return is absolutely impossible in the narrowest sense, but because the energy cost, shielding burden, mission duration, support limitations, and lifespan constraints pile up until the difference between possible and not realistically happening stops mattering. That is one of the central truths of this whole video. The solar system is not a set of airports where every destination is just farther away than the last. It is a gradient. At one end, departure is hard, but return is still realistic. Then the distances grow, the support weakens, the risks accumulate, and return becomes less secure, less likely, less timely, and less meaningful. At some point, you are no longer talking about travel in any ordinary sense. You're talking about practical non-return. That is what beyond Mars really means. Not just bigger numbers, but a changing category. A place where the map still has roots on it in theory, but where each outward step makes the line back to Earth thinner, more fragile and more dependent on conditions that may not survive the mission. So by now the pattern is clear. Gravity made leaving hard, biology made survival unstable. Radiation kept working against you the whole time. Distance erased rescue. Time pulled you out of sync with Earth. Mars pushed return to the edge, and beyond Mars, the solar system starts turning into a place where outbound movement remains imaginable, but inbound return starts fading into a technical hope more than a practical plan. And if even the solar system can do that, then the next step ends the debate completely. Because once you start talking about other stars, coming back is no longer a difficult goal, it is almost a contradiction. Interstellar travel ends the debate because the scale alone destroys the idea of return. The moment you say another star, the whole conversation changes category. Inside the solar system, return can still be discussed as a hard engineering problem. Beyond the solar system, return starts collapsing under distance alone. The nearest star system, Alpha Centauri, is about 4.37 light-years away. 1 light-year is about 9.46 trillion kilometers, or roughly 5.88 trillion miles. Those are numbers so large that normal human intuition stops working. They do not feel like travel distances. They feel like something closer to geological or cosmic separation. And here is the part that makes the point immediately clear. Even if you could move at 10% of light speed, which is vastly beyond anything humans can currently do with crude spacecraft, the trip would still take decades one way, and that is before you even fully count the acceleration and deceleration phases. So at the very first realistic glance, the old idea of go there and come back is already broken. Not because someone made a rule against it, but because the scale itself crushes the meaning of a normal mission. That is why interstellar travel is not just farther space travel, it is a different kind of problem entirely. The distances are so large that the timescale of a human life starts becoming one of the central constraints. And once a trip is measured in decades or longer each way, return has already stopped behaving like a normal outcome. Then the next hard reality arrives immediately after that. Chemical rockets are nowhere near enough. Chemical propulsion is what got humans to the moon, and that only worked because the moon is practically an Earth's front yard by cosmic standards. Chemical rockets are useful for leaving Earth and moving around the inner solar system in very limited ways, but for interstellar missions they are hopelessly inadequate. The energy requirements are too large, the propellant demands become absurd, and the travel times remain crushing even before you solve the other survival problems. So once people seriously talk about interstellar missions, the conversation usually shifts into technologies that do not exist in operational human form. Fusion propulsion, antimatter, beam-driven sails, cryogenic preservation, generation ships, or some future physics breakthrough we do not have, and that is a very important boundary. Once your mission depends on technology that is still speculative, incomplete, or not fielded at the scale required, then return is no longer a real plan. It is a story about what might happen if multiple impossible-seeming things all become possible at once. That distinction matters. A plan is something you can engineer around known capability. A story is something you tell because the capability is missing. An interstellar return lives much closer to story than to plan with anything humanity currently knows how to build. Then there is one of the darkest versions of the idea, and also one of the most realistic if anyone ever seriously tries this. Generation ships make home biologically meaningless. If a voyage takes centuries, then the people who arrive are not the people who left. Multiple generations would be born, live, and die on board. The society on that ship would become its own world long before arrival. At that point, return to Earth stops making sense in any personal way. Nobody on the original departure crew comes home because they are long gone. Even if descendants someday travelled back, they would not be returning home in the human sense. They would be travelling to an ancestral origin, to a place known through records, stories, and identity, not memory. That is a major shift in meaning. Interstellar travel turns non-return from a mission risk into the mission model. The mission is not, we go there and come back. The mission becomes, we leave, and our descendants live inside the consequences. Once that is true, the old language of exploration is already obsolete. You're no longer discussing travel in the ordinary sense. You're discussing civilizational branching. And then even the one thing people sometimes treat like a loophole ends up making the argument stronger, not weaker. Relativistic travel introduces new kinds of separation. At high fractions of light speed, relativistic effects become important. Time would pass differently for travelers than for people who stayed on Earth. The crew might experience less elapsed time than Earth does. At first, that sounds like a clever workaround. It sounds like maybe you could go very far, come back, and avoid losing as much of your life. But emotionally and historically, it makes the separation even more final. Because now, the cost of the trip is not only distance, it is time divergence. You could leave, age modestly relative to your own onboard clock, and still return to an Earth that is centuries older. Everyone you knew would be gone. Every institution you launched under would be gone. Every cultural reference, every language shift, every social structure would have moved beyond your world. You would not have beaten non-return. You would have turned it into a precise physical fact. That is why relativity does not rescue the idea of coming back. It changes the mechanism of separation, but the separation remains. In some ways, it becomes even more absolute, because now physics itself helps formalize the break between your timeline and Earth's timeline, and that leads directly to the final point of the whole section. Crossing between stars is really crossing out of human reciprocity. As long as missions stay near Earth, there is still some two-way relationship. Earth can resupply, Earth can monitor, Earth can sometimes rescue, Earth can still matter in real operational time. Maybe for the inner solar system, enough infrastructure could extend some of that relationship farther. But interstellar travel breaks it completely. No rescue that matters, no timely supply, no real-time command. No cultural synchronization. No practical return, no stable two-way exchange where Earth remains an active partner in the mission. Once you cross that distance, Earth stops being your support system in any meaningful operational sense. It becomes an origin point, a memory, a signal source from the deep past. That is the final upgrade of the argument this whole video has been building. Leave Earth far enough and back stops existing as a serious concept. Not just because the trip is dangerous, not just because the body is fragile, not just because rescue fails, but because the entire structure that makes return meaningful collapses under scale, time, technology limits, and the end of reciprocity. That is what interstellar travel really exposes. It takes every problem we have already covered: gravity, biology, radiation, distance, timing, isolation, and then stretches all of them until the word return becomes almost dishonest. There may still be trajectories pointing toward Earth on a map. There may still be theoretical pathways in equations. But for human life, culture, and mission design, something much more important has disappeared: the practical existence of coming back. So by the time you reach this point, the title of the video is no longer just a dramatic claim. It has become a direct statement about what scale does to meaning. Within the solar system, return gets weaker the farther you go. Between stars, it breaks entirely. And if crossing to another star already destroys the idea of a real return, then the final step is even more unsettling. Because now we have to face a truth that applies even to shorter missions, even to successful missions, even to people who physically land again. Earth itself will not stay the same while you are gone. Earth does not wait for you, and that means even a successful return is still a return to something different. This point sounds simple, but it changes the whole meaning of coming back. People talk about Earth like it is a fixed place, like home is just sitting there unchanged while the mission happens somewhere else. That is not true. Even short missions return to a changed planet. Technology changes fast now, sometimes in years, sometimes in months. Institutions get replaced or weakened. Infrastructure evolves. Media ecosystems change constantly. A crew that leaves Earth and comes back later is not returning to the same human world it left. That matters more than it seems. A deep space traveler could come home to different systems, different tools, different assumptions, different priorities, different public and different kinds of daily life. The world does not preserve itself for returning explorers. Earth is dynamic. Home is moving. So even before you start talking about very long missions, the idea of a perfect return is already breaking. You can come back to Earth, but not to the exact Earth you launched from. And when you stretch the timeline out, that change becomes even more literal. Over longer timescales, geology and climate keep rewriting the stage. Earth's continents drift over millions of years. Climate changes over both short and long timescales. Sea levels rise and fall, ecosystems collapse, shift and rebuild. Species disappear, new ecological patterns emerge. Human civilization changes the planet, then suffers the effects of those changes, then changes it again. So even at the planetary level, Earth is not fixed scenery. It is an ongoing process. That matters because people often talk about Earth like it is the one constant in the story, the stable background everything else is measured against. But Earth is not a still background. It is active, changing and unstable across time. A mission does not leave one permanent world and then return to that permanent world later. It leaves one temporary version of Earth and comes back to another temporary version. That is already true on human timescales, but then the argument goes even deeper. The sun guarantees that the familiar Earth does not last forever. The sun slowly brightens over geological time. Long before it becomes a red giant, the increasing energy output will change Earth's climate in major ways. On billion-year timescales, the surface habitability of Earth changes profoundly. That means there is no eternal Earth waiting in the background of the universe. The planet you know is not permanent, it is a phase. This is important because it strips away the last comforting idea that Earth is the fixed point you can always come back to in the deepest sense. It is not. Every departure from Earth is a departure from a temporary world. The oceans, the atmosphere, the climate, the biosphere, the human-built systems, all of it exists inside time. None of it is frozen. None of it waits forever. So by this point, coming back is already starting to fail at multiple levels at once. The society changes, the planet changes, the long-term habitability changes, and then there is another systems point that makes the whole thing even less secure. Human return depends on civilization continuing. This is the darker part people usually leave out. A spacecraft can survive re-entry, but that is not enough by itself. A returning crew still needs a civilization below that can track them, recover them, treat them, repair equipment, interpret systems, provide medical care, and reintegrate them. Earth is not just a surface to land on, it is an active support network. That means a successful return still depends on that network existing in a usable form. If civilization changes enough, weakens enough, fragments enough, or simply stops caring about the mission that left long ago, then returning physically is not the same as truly being received. A capsule could come down to a world that is technically still there, but operationally not the same world at all. That is one of the most serious ways the word return misleads people. It makes it sound like the only thing that matters is trajectory and landing. But real return depends on continuity. It depends on a living society that can absorb the people coming back. If that continuity breaks, then home is no longer functioning in the way the word suggests. And that leads directly to the hardest line in this whole section. You never come back to the same Earth because there is no same Earth. That is not vague, and it is not just poetic. The Earth you leave is a specific arrangement of matter, institutions, relationships, memory, biology, and time. By the time you return, that arrangement is gone, maybe only slightly gone after a short mission, maybe radically gone after a long one, but gone either way. That is why the title of the video stops being just a dramatic claim and becomes literal in a deeper sense. Never come back is not only about dying in space, missing a return window, or being trapped on another world. It is also about the fact that the exact Earth you left no longer exists by the time you arrive. Not socially, not historically, not biologically, not even planetarily if you stretch the timescale far enough. So this is where the argument tightens again. You leave Earth and your body starts changing, you go farther and rescue fades. You stay away longer and time pulls you out of sync, you go deeper and return becomes fragile. But even if everything works, even if the vehicle lands, even if the crew survives, Earth itself has moved on. The place you are returning to is real, but it's not the same world you departed from, and that means the phrase coming back has been unzippable from the very beginning. It sounded solid only because people were treating Earth like a fixed point when it was never fixed at all. And if Earth itself is changing too fast for return to ever be complete, then the next section goes even more personal, because now we have to face the fact that even if you land again, you do not return as the same human being who left. The real barrier in space is not just distance, it is dependency. Distance is the part people can see. They can picture millions of kilometers, long travel times, communication delays, launch windows. But dependency is the part that actually controls survival. Because the deeper truth is this: a human habitat in space does not become safe just because it reaches the destination. It stays alive only as long as an artificial life support system keeps winning every hour of every day. Every habitat has to regulate air, water, temperature, waste, pressure, and power. On Earth, those functions are not handled by one machine in one room. They're handled by a whole planet. Earth runs these cycles through oceans, atmosphere, ecosystems, geology, weather, biology, and huge natural feedback systems. In space, you do not get any of that for free. You have to rebuild enough of it inside a sealed environment using hardware and maybe biology, and it all has to keep working. That is why living off Earth is really living on life support debt. Every day you're alive in space, you're depending on systems that must continue performing without major failure. If they fail, that is not a bad day or a temporary disruption. It is immediate danger. Failure is not inconvenient, it is terminal. That is a very different kind of existence from life on Earth, where the planet absorbs shocks for you all the time without you noticing. And this is where the next misconception has to be cut out clearly. Closed-loop systems are impressive, but they are still incomplete. People hear about water recycling on space stations and assume we are already most of the way to self-sustaining space habitats. It is true that these systems are impressive. Water recovery can be very efficient. Air revitalization systems are advanced. Food experiments are ongoing. But none of that means we have solved the problem of truly independent human life away from Earth. A long-term closed ecological life support system that can reliably sustain large human populations without massive resupply is still one of the hardest unsolved problems in space settlement. That is the important scale people forget. Running a station with a small crew for a limited time is one thing. Sustaining a city or a permanent settlement with minimal outside input is something else entirely. Earth solved this problem over billions of years. Earth is a giant, evolving, self-maintaining life support system. What we are trying to do in space is compress enough of that stability into machines, tanks, filters, growth chambers, recycling loops, and maintenance routines. That is not impossible in principle, but it is nowhere near trivial, and it is nowhere near complete. So when people talk about just building habitats, they're skipping over the fact that a habitat is not just a shell with people inside it. It is an attempt to replicate enough of a planetary system to stop the occupants from dying. That is a much harder thing to build than the word habitat makes it sound. Then there is another issue that becomes brutal once missions get long. Spare parts are frozen time. Every component you bring is a prediction about the future. You are guessing what will fail, how it will fail, when it will fail, and what you will need to repair it. That means your survival is partly tied to how well you predicted problems before launch. If something breaks that you did not expect, then suddenly your distance from Earth is no longer measured in kilometers or miles. It is measured in missing tools, missing materials, missing replacement parts, and missing manufacturing capability. That is a serious shift, because it means remoteness is not just about geography. It is about being unable to make what you need when the wrong thing fails. Additive manufacturing can help. Smarter diagnostics can help. Autonomous repair may help even more in the future. But right now, true self-sufficiency in space remains mostly a horizon, not an achieved reality. That means every habitat is living partly inside a frozen inventory. You launch with a set of assumptions, and then you hope reality stays close enough to those assumptions for long enough The farther away the habitat is, and the longer it has to operate, the weaker that hope becomes. Because time creates surprise, and surprise is exactly what sealed systems hate most. And this leads to the most important comparison in the whole section. A city on Earth is plugged into a planet. A base in space is unplugged. A city can lose power and still call in outside help. It can import food, it can bring in water, it can evacuate patients, it can draw on regional and national infrastructure. It can reroute supply chains, it can rebuild damaged systems with support from other cities, other industries, other continents if needed. A city is not self-contained. It survives because it is connected to enormous surrounding capacity. A base on Mars or in deep space does not have that. It cannot casually import what it forgot. It cannot assume backup is nearby. It cannot depend on a giant living world and a giant industrial civilization to quietly stabilize every crisis. It is much closer to a submarine that never surfaces and can never count on rescue. That is not what most people picture when they hear words like colony, base, or settlement. Those words sound stable, but the actual system is far more fragile. That is why a lot of early off-world living may be better described as sustained emergency management. Not because disaster is happening every minute, but because the margin for disaster never goes away. The systems that keep people alive are always critical, always active, and always one layer thinner than the systems people on Earth live inside. And once you understand that, the last point becomes much more powerful. Dependency is one reason the first outward human communities may become permanent by accident. Not because anyone officially planned exile, not because everyone chose one-way missions in some dramatic moment, but because every year away pushes a settlement toward more local autonomy, more local manufacturing, more local food production, more local repair, and more local adaptation. That sounds like progress, and in one sense it is, but it also changes the relationship with Earth. Eventually, a community can become more compatible with staying than with returning. Its systems are built around local survival, its people are adapted to local routines, its infrastructure is designed for continuity where it is. At that point, Earth is no longer the operational centre of life for those people. The break becomes real, even if nobody announces it, and that is one of the deepest truths in the whole video. The real barrier is not just how far away a place is, the real barrier is how much of Earth you still need, how well you can replace it locally, and what happens when your local system becomes good enough to keep you there, but not good enough to send you back easily. That is why dependency matters more than distance in the long run. Distance is a map problem, dependency is a civilization problem. Dependency decides whether people off Earth are temporary visitors, fragile outposts, or populations slowly drifting into permanent separation from the planet that made them. So by this point, the structure of the trap is almost complete. Space does not have to physically forbid return. It only has to make survival depend on local systems so demanding, so fragile, and so self-contained that staying becomes more realistic than leaving. And if that is true at the systems level, then the next section makes it personal again, because even if you do land back on Earth, there is still one final break left to confront. You do not return as the same human being who left. Landing on Earth again does not mean you return as the same human being. This is the last personal layer of the argument, and it matters because people still hold on to one final comfort. They may accept that return is hard, risky, expensive, delayed, and incomplete. But they still imagine that if the astronaut physically lands, then in the deepest sense the person has come back. That sounds reasonable until you look closely at what space does to body, mind, and identity. Space changes identity through perspective before it changes anything else you can measure. Many astronauts describe something called the overview effect. They look at Earth from space and see one small, fragile world hanging in darkness. That is not just a dramatic description, it is a serious cognitive shift. On Earth, you grow up with the planet as background. It is the ground beneath you, the normal frame of reality. From space, it stops being background and becomes an object, a whole world finite and exposed. Once someone has seen that directly, ordinary life may not look the same again. Daily arguments can feel smaller. the scale of environmental fragility can feel much more immediate. The person is still the same person in one sense, but the internal map they use to think about life has changed. They can re-enter the atmosphere, but they cannot fully re-enter the old mental framework they had before seeing Earth from outside it. That's the first quiet break in the meaning of return. A person comes back to the same streets, the same rooms, the same language, but with a different mental relationship to all of it. And that is before we even talk about the more physical changes, because the body may not fully undo what space did to it. Some adaptations recover, some recover slowly, some may not recover completely. Bone density can take a long time to rebuild, and some losses may not be fully restored. Visual changes can persist. Balance problems can continue during recovery. Cardiovascular deconditioning can make gravity feel harder than it used to. Chronic stress can leave longer marks than mission summaries usually admit. That is why the simple fantasy of go to space, land, and step back into normal life does not match reality. After enough time away, normal life is not sitting there ready to restart at full strength. Gravity itself becomes something your body has to handle again. Standing, walking, stabilizing posture, moving naturally, all of it can require readaptation. Home gravity becomes something you have to re-earn. That phrase matters because it shows how far the body can drift from its baseline. Earth is not just where you come back to, it becomes a condition you have to recover for. And once that is true, the idea of a clean return already starts falling apart on the level of daily human experience. Then there is another kind of drift that matters just as much. Relationships on Earth do not freeze because you left. Family changes, friends change, institutions change, cultures change, roles change. Even without space travel, people already know this in smaller ways. Long deployments, submarine service, polar expeditions, long illness, migration, all of these can create a feeling that the people involved did not move through time together. Deep space would amplify that to an extreme. The deeper the mission, the stronger that divergence becomes. You come back to relationships that developed without you. People adapted to your absence. They formed new routines, new expectations, new priorities. Children grew, parents aged, colleagues moved on, institutions reshaped themselves. The emotional ground under your life is no longer exactly the same. That means return is not just about getting your own life back. It is about discovering that other people's lives did not pause for your mission. They kept moving. And once enough time passes, the reunion is real, but the old alignment is gone. You return to altered relevance, altered intimacy, altered context. You are still connected, but not in the same way. And then the next point is where the unease becomes more serious. You may become more adapted to the mission than to the planet. This is one of the hardest truths about long-duration exploration. Human beings adapt to routines, constraints, and environments faster than people like to admit. A spacecraft or habitat may be hostile in one sense, but if you live inside it long enough, its structure starts becoming your version of normal. The sounds, the schedules, the procedures, the limits, the narrow spaces. The mission focus, all of it can become familiar in a way Earth no longer is. So when you return, Earth can feel noisy, heavy, crowded, wasteful, chaotic. Not because Earth changed into something impossible, but because your nervous system spent so long learning another pattern of life that this one now feels less natural than it used to. You do not just bring memories of space home with you. Space can become the environment your mind and habits were most recently built around. That is the quiet terror underneath long missions. The person who returns may in some ways be better matched to the mission than to the world the mission started from, and if that happens, then return becomes even more incomplete. You are physically home, but your internal sense of normal may still belong somewhere else. And that leads to the final human level point. Return without restoration is not really return. This is where the myth finally breaks. People often act as if survival plus touchdown equals success. The capsule lands, the hatch opens, the crew is home, but if the body changed, the mind changed, relationships changed, civilization changed, and the world itself kept moving, then what exactly has returned in the full sense people usually mean? A person can come back physically and still never fully come back in the deeper sense this title is pointing toward. They may stand on Earth again, but not with the same body. They may see family again, but not in the same emotional world. They may resume life, but not with the same assumptions or identity. The physical journey may close, but the human separation does not fully reverse. That is why this section matters so much. It takes the argument out of hardware and physics and makes it impossible to ignore on the level of one person. Even if the mission goes well, even if the return vehicle works, even if re-entry succeeds, something important still stays changed. The human being who left Earth does not come back in exactly the same form. The old body is gone partly. The old map of reality is gone partly. The old place in time is gone. The old relationships are gone in their original form. So by now the structure is complete. Leaving Earth changes your biology, strains your systems, weakens rescue, stretches time, increases dependence, and can slowly make you less synchronized with the planet you came from. Then even a successful landing fails to restore what was lost, and that means the final section no longer has to prove much. It only has to say plainly what everything has already been building toward. Leaving Earth is leaving the condition that made you possible. Earth is not just one planet among many for humans, it is the condition that made humans possible. That is the final truth this whole argument has been moving toward. People often talk about Earth as if it is just our starting point, one world among many, the first home before we move on to others. But for human beings, Earth is not just home in that casual sense. It is the baseline of all baselines. It is the place where gravity, atmosphere, magnetism, water, chemistry, biology, and history all line up in the exact combination that produced us. That matters because every other place we can reach is hostile by default. Not difficult by default, hostile by default. Space does not begin as a place where humans can live and then become easier with technology. Space begins as a place where humans die unless technology keeps rebuilding enough of Earth around them every second. That does not mean we should never go, it means we should stop pretending that going is simple, reversible, or normal in the way travel on Earth is normal. That is the part people keep softening. They want exploration to sound safe, clean, and controlled. But the real meaning of leaving Earth is much bigger than that. It means stepping outside the one environment that shaped every system inside your body and every structure underneath your civilization. Once you say it that way, the real scale of the act becomes clear. And that leads to the next point. Because exploration only has its real weight if we stop lying about the risk. Exploration is real precisely because return is not guaranteed. That is not pessimism. That is the reason exploration matters at all. If leaving Earth were easy, fully reversible, and biologically harmless, it would not feel profound, it would just be transport. The grandeur of exploration comes from asymmetry. It comes from the fact that crossing outward changes you, endangers you, and may not let you come back in the way you expected. The deeper we go, the more each mission starts looking less like a trip and more like a boundary crossing. That is why people care so much about space in the first place, even when they do not say it clearly. They understand at some level that leaving Earth is not just motion. It is transformation under risk. It is not ordinary because it cannot be made fully ordinary. So the honest version of space exploration is not smaller than the comforting version. It is bigger. It is more serious. It matters more because it asks more of the people who do it. The danger is not a flaw in the story, it is the reason the story has weight. And then the next truth becomes unavoidable, because if leaving Earth changes people that much, then humanity's future off Earth cannot just be a copy of life here. Humanity may spread beyond Earth, but not as unchanged Earthlings. Moonworkers may exist, Mars settlers may exist, orbital populations may exist, deep space crews may exist. Maybe one day even interstellar descendants will exist, but they will not simply be us somewhere else. Different gravity, different radiation levels, different delays, different economies, different birth conditions, different generations growing up under different limits. All of that will create divergence. This is one of the most important things to understand. Expansion into space is not duplication, it is branching. Human life away from Earth will not remain a perfect copy of Earth life forever, because the conditions will not remain the same forever. The systems will evolve differently, the cultures will evolve differently, the bodies may adapt differently over long enough timescales, the priorities will certainly evolve differently. So when people talk about humanity moving into space, they often picture the same civilization just stretched across more locations. But that is not what the logic of the environment suggests. The more realistic picture is branching, separation, and divergence. New human communities may grow beyond Earth, but they will not remain exactly identical to the world that produced them. And once that is clear, the main phrase of this video starts sounding much stronger than it did at the beginning. The phrase "never come back" is scientifically stronger than it first sounds. Physically, many missions may never return because energy, distance, radiation, logistics, hardware failure and timing can cut the route home. Biologically, even successful crews may not fully readapt. Historically, Earth will have changed while they were gone. Psychologically, their identity may have shifted too far to fit cleanly back into the life they left. Civilizationally, communities beyond Earth may become permanent because local survival eventually matters more than going home. And cosmically, the farther outward you go, the less meaningful the word back becomes at all. That is why the phrase is not just dramatic language. It is a compressed summary of multiple real processes happening at once. You may return physically and still not return biologically in full. You may return biologically and still not return historically. You may preserve both body and memory and still find that civilization moved on. Or you may go far enough that return stops being a serious concept in the first place. So by now, the statement has widened far beyond simple mission failure. It is no longer just about whether a spacecraft can make the trip in both directions. It is about whether the full original relationship between person, planet, body, time, and civilization can be restored. And the answer, again and again, is no. So here is the final line this entire video has been building toward. The instant you leave Earth, you begin a separation that no engine can fully reverse. You can fall back through the atmosphere. You can survive re-entry. You can land. You can splash down. You can stand again under blue sky and breathe again under open air. But that does not mean everything came back with you. The planet that made you will have changed. Your body may have changed. Your place in time will have changed. Your relationships will have changed. Your mind may have changed. And if you go far enough, even the meaning of home changes with it. That is the real point. Coming back is not one thing. It is many things layered together, and space starts pulling those layers apart the moment you leave. Physics separates you. Biology separates you. Time separates you. History separates you. Distance separates you. Eventually, even identity separates you. And that is why anyone who leaves Earth never really comes back. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.